Hello everyone, this is your course instructor Monisha Raj KH, Assistant Professor, Department of ECE, Sai Vidya, Institute of Technology. In this lecture video, we'll be starting with Module 5 of Information Theory and Coding, that is Convolutional Codes. Before going into depth of Module 5, first we'll see the contents in Module 5, and it goes as follows. The first one is Convolutional Encoder, which is followed by two approaches. That the first one is time domain approach, the second one is transform domain approach. Next, this is followed by code tree, trellis, and state diagram related to convolutional codes. And the last topic is the Viterbi algorithm. So before going into depth, that is about the convolutional encoder, first we need to know the basic difference between the block codes and the convolutional codes. About block codes, we have already studied in the previous modules. So in this module, we'll be concentrating mainly on convolutional codes. So let us see the basic difference between the block codes and the convolutional codes. The main difference between the block codes and the convolutional codes is that in block codes, a block of n digits generated by an encoder in a particular time unit depends only on the block of k input message digits within that time unit. But in convolutional codes, a block of n code digits generated by the encoder in a time unit depends not only on the block of k message digits within that time unit, but also on the preceding m-1 block of message digits. Hence, m should always be greater than 1. Like block codes, convolutional codes can be designed to either detect or correct the errors. But block codes are mainly suited for error detection, and the convolutional codes are better suited for error correction. Encoding of convolutional codes can be accomplished using simple shift register, and decoding is done using several practical procedures. After knowing the basic difference between the block codes and the convolutional codes, we'll move on to the encoder for convolutional codes. As we have studied in the previous modules, in block coding, the encoder accepts a k-bit message block and generates an n-bit code word. Thus, the code words are produced on a block-by-block basis. Clearly, provision must be made in encoder to buffer an entire message block before generating the associated code word. But there are applications, however, where the message bits come in serially rather than in large blocks, in which case the use of buffer may be undesirable. In such situations, the use of convolutional coding may be preferred method. A convolutional encoder operates on the incoming message sequence continuously in a serial manner. The encoder of a binary convolutional code with a rate 1 by n measured in bits per symbol may be viewed as a finite state machine that consists of an m state shift register with prescribed connections to n modulo 2 adders, and a multiplexer that serializes the outputs of the adders. An L-bit message sequence produces a coded output sequence of length n into L plus m bits. The code rate is therefore given by R equal to L by n into L plus m bits per symbol. Typically, we have L very much greater than m. Hence, the code rate simplifies as R approximately equal to 1 by n bits per symbol. The constraint length of a convolutional code expressed in terms of message bits is defined as the number of shifts over which a single message bit can influence the encoder output. In an encoder with an M stage shift register, the memory of the encoder equals M message bits, and capital K equal to M plus 1 shifts are required for the message bits to enter the shift register and finally come out. Hence, the constraint length of the encoder is represented as capital K. After knowing the gist about the convolutional encoder, next we will be seeing about the block diagram of the convolutional encoder. The figure shown in the slide shows a convolutional encoder with small n equal to 2 and capital K, that is the constraint length, equal to 3. Hence, the code rate of this encoder calculated will be 1 by 2. The encoder in the figure operates on the incoming message sequence, that is, 1 bit at a time. We may generate a binary convolutional code with a rate equal to k by n by using k separate shift registers with prescribed connections to n modulo 2 adders, an input multiplexer and an output multiplexer. This is the generalized convolutional encoder. Now, to understand this better, we'll be considering an example in the second diagram shown in the figure. An example of such a encoder, that is the first diagram encoder, is shown in the second diagram, where small k equal to 2, n equal to 3, and two shift registers are the constraint length capital K equal to 2 each. By using these values, the code rate is calculated as 2 by 3. In this example, the encoder processes the incoming message sequence to be 2 bits at a time. The convolutional codes generated by the encoders, as shown in these two figures, are non-systematic codes. Unlike block coding, where we've studied about the systematic codes, the use of non-systematic codes is ordinarily preferred over the systematic codes in convolutional coding. So in block codes, we will be using systematic codings, but in convolutional codes, we'll be using non-systematic codes. So we will use this encoder to illustrate the theory of convolutional encoders by using two approaches. Which are those two approaches? One is time domain approach and the second one is transform domain approach. So about these two approaches, that is time domain approach and transform domain approach, we'll be studying in next video. Thank you.